Hi everyone, I'm Shelbenalidis, and in this video, I'm going to explain the basic ideas of Einstein's general relativity. So, what actually the general relativity is? Well, Einstein discovered that gravity is not actually a force. Instead, it is what happens when heavy objects like planet or star bend the space and time around them just like a heavy ball bend a rubber sheet. Because space is curved, things like lights and planets follow curved paths. These paths are called geodesic, the straightest possible path in curved space. When light curves around a massive object, we call that gravitational lensing, and it's a real proof that space is actually bending. General relativity also tells us that time moves differently in strong gravity. A clock near the surface of Earth runs slightly slower than a clock far away in space. This effect is called time dilation, and it was confirmed by scientists in 1959. One of the most useful applications of general relativity is the GPS system. Satellites are farther from Earth and move faster, so their clocks tick differently. Without instant correction, GPS location would be wrong by up to 10 kilometers per day. However, general relativity doesn't work well when things get extremely small, like inside black holes or at the moment of the Big Bang. That's why scientists are trying to create a new theory called quantum gravity to connect Einstein's idea with rules of quantum physics.
Hi, my name is Sabrina and I'm in charge of the quantum gravity. Have you ever wondered what is quantum gravity? Quantum gravity attempting to unify two major theories, quantum mechanics and general relativity. Quantum mechanics govern the tiny world of atoms and particles, while general relativity explains how gravity works on large scale. So what is the problem? These two theories doesn't work well together, especially in extreme places like black holes or the Big Bang. Relativity says that black holes have infinite curvature, but quantum mechanics says that particles can be in multiple states at once. So which one is right? That's what quantum gravity hopes to figure out. Since we can't test this directly in lab, scientists use thought experiment and advanced theory like M-theory and loop quantum gravity to explore it. Despite limitations like gravitational singularities and dark matter, scientists remain determined to solve this challenge. Quantum gravity challenges our understanding of the universe, combining quantum mechanics and general relativity. While we still haven't all the answers, each discovery brings us closer.
So hi everyone, my name is Azri Izzati binti Azli, and today I will explain why there is a conflict between general relativity and quantum gravity. These two of the most important theories in physics. General relativity or GR describes gravity as the smooth curvature of space-time. It works extremely well for large-scale systems like planets or GPS. Its framework is classical field theory, and it predicts singularities where place physics breakdowns like black hole and the Big Bang. Quantum gravity or QG, on the other hand, tries to apply quantum rules to gravity. It assumes space-time is not smooth but discrete, quantized at incredibly tiny scale called the Planck scale. It also tries to fix singularities by using quantum effects. The main problem here is GR treats space-time as dynamic. It can bend and evolve, but quantum theories usually need a fixed background to work. This creates a major incompatibility. Also, GR has been well tested in experiment, but QG is very hard to test because it involves extreme energy scales we can't easily reach. In conclusion, this conflict exists because GR and QG have very different views of space-time, and solving this difference is one of the biggest open problems in modern physics. Thank you.
Hi, my name is Amni Afika. My part of the project focuses on string theory, a fascinating idea that could help unify physics. String theory suggests that the smallest building blocks of nature aren't tiny dots, but tiny vibrating strings. Everything including electrons, photons, even gravity comes from this vibration. Just like guitar strings play different notes, each vibration creates a different particle. A photon might be one vibration, a quark another, just like music at a smaller scale. But here's the twist. These strings don't just vibrate in our usual 3 dimensions. They move through up to 10 dimensions that we can't even see. String theory is one of the main ideas trying to connect Einstein's theory of gravity with the quantum mechanics. It's a strong candidate for a complete theory of quantum gravity, the one that explains everything. Even though it's not proven yet, string theory could help us understand black holes, the Big Bang, and the nature of the universe. It's physics, but it feels like music.
Hi there, I'm Nur Alia Akila binti Roslin, and today I'll take you on a quick journey into one of the most mind-blowing theories in physics, which is loop quantum gravity. We usually think of space as empty and smooth, but maybe that's not true. Maybe space is made of something tiny and hidden. That's the big question behind loop quantum gravity. These tiny loops does not float alone. They're connected. Together they form a network like a web or fabric. This is called a spin network. Space is made not just empty, but built by loops. Einstein said gravity is the bending of space, but loop quantum gravity says the bending comes from the loops. Some scientists think everything is made of tiny strings, but that's string theory. Others think space is made of loops, and that's for loop quantum gravity. String vibrate, loop spin and link. Both are searching for the same answer, which is what is the universe made of? We don't know everything yet. The universe is full of questions, but every new idea helps us understand more. Maybe it's loops, maybe it's something else. One thing is sure, the journey to discover space and gravity is still going.
Hi everyone, I am Alia Christina and I'm in charge of the topic Future Applications of Quantum Gravity. Quantum gravity explores how gravity works at quantum scales, which something classical physics like general relativity can't fully explain on its own. One of the future applications is quantum gravity on quantum chips. These chips could help scientists simulate complex systems, giving deeper insights into how the universe behaves. This can lead to more accurate models in physics and even open new doors in advanced computing. Another exciting direction is combining machine learning with quantum gravity. This helps researchers analyze quantum matter faster and more efficiently by training algorithms to detect patterns. There is also ongoing development of quantum sensors, which are devices that rely on the quantum principles like entanglement and superposition for ultra-sensitive measurements. These sensors have the potential to detect dark matter and could be used in future experiments involving gravity and fundamental particles. Lastly, quantum gravity has promising uses in space exploration. NASA is working on quantum-based navigation sensors that can help guide spacecraft more precisely. In short, these future applications show how quantum gravity is more than a theory. It is a growing field that could change how we explore space, build technology, and understand our universe.